And so, yeah, as you mentioned, I have spent the last 5 or so years of my life trying to bridge the gap between experiments and computations through looking at dynamics of charge carriers, photo-excited charge carriers, and lead halide perovskite nanocrystals. And so, to give a brief overview, so the presentation will go as a brief overview of nanotechnology and material science involved in optoelectronic devices, which is the main application for these lead halide perovskites. And then I'll give a little overview of the computational methodology so that the theorists can have a way to communicate with each other. And then the last part of the presentation will be three independent studies on photophysics of the lead halide perovskite nanocrystals. And so, to start with, what are optoelectronic devices? So one of the most common ones are photovoltaics and LEDs, which are both a part of, can be considered as photodiodes. And they work in similar ways. So for photovoltaics, they generate photovoltages due to irradiation. So it converts light into electricity. And it can be used as a clean source of sustainable energy, whereas there's plenty of sunlight irradiating the surface at one time. And in contrast, LEDs basically work in the opposite. So they convert electricity into light. And it's been shown that they've been more efficient than incandescent bulbs, which rely on heating the material, whereas with LEDs, you can tune the emission based on the material in the device. And so for photodiodes, they have very similar device architectures, which are illustrated and color-coded in this slide. So they're made up of a photoactive material, which generate charges or as recombination centers. And those are the yellow materials. So on the left is an energy diagram illustrating how a solar cell would work. And on the right is a cartoon of a device architecture and layers. So in energy, after a photo excitation, you want the electron and hole to separate from each other so they don't recombine. So the electron, you hope, diffuses to a transport layer, which separates it from the hole, which diffuses to the whole transport layer. And they migrate in energy lower and lower until they reach the contacts and you can run them through a circuit. And then LEDs work essentially if you reverse all the arrows in a similar way. And so the main activity of this research will be focusing on these photoactive layers and materials we can use for them. And specifically for solar cells, there are known limitations to photovoltaics just based on thermodynamic arguments and electronic processes that happen in the material. And so there are generally two assumptions. So you can have, or one of the assumptions is that energy above the band gap is lost as heat due to thermalization. And the second assumption is that for every one photo excitation, only one charge carrier is created. And so with those, I guess I'll illustrate assumption one using a cartoon. So for semiconductors, they have a generalized band gap, which between the conduction and valence bands. And when it's irradiated by sun, there are a distribution of frequencies spanning from redder to bluer. And if the energy of the light is below the band gap, that won't be turned into energy because it's too low to bridge the conduction and valence band. But if the light is too blue, like you'll have energy of excess of the band gap, and all the energy above the band gap, so the green region minus the black region, will be lost as heat. And so you can average over all these, you can generate a figure something like this. So it plots the amount of energy you can get out of a solar cell as a function of the semiconductor band gap. And you can see that it reaches a maximum at around 1.5 eV, where you can get it like 33%. So that's considered like a theoretical maximum for conventional solar cell material like bulk silicon. And the losses are illustrated here, and you can see that there's a lot left on the table due to these thermalization processes in the green and the lost energy due to not being able to absorb in the pink. So ideally, we would like to be able to increase the area of this black region to get more efficient solar cells. And that leads into the role of nanotechnology in optoelectronic devices. So I'll give a brief overview of nanomaterials in general. So a prototypical example for nanomaterials are the fullerenes, which are just pure carbon-based compounds. And so you can consider graphite, which is the lead in your pencil, and it's essentially made of a bunch of layers of 2D carbon sheets. And so you can take Scotch tape and peel away at the graphite, and if you're lucky enough, you can produce a single layer, which is considered graphene, and it's considered a 2D material because it's literally an atom thick, while the other two dimensions are much, much longer, on like micrometer scales possibly. And so you can imagine if you have a sheet graphene, you could roll it up into a tube and make something like a rod. And those are known as carbon nanotubes, which are a 1D material where the radius of the tube is on the nanometer scale and its length scale is on much, much longer length scales. And for 0D material, you can imagine wrapping that graphene into a ball. And those are known as buckyballs, where the radius of the ball is on the nanometer length scale. And specifically, I'll be focusing on these 0D nanomaterials. And they can be composed of different chemistries. And for semiconductors, a common architecture looks like this image here. And so it's made up of two components. So you have an inorganic semiconducting core, which is these bronze regions. You can see the pixelated crystal faces on there, which make up the semiconductor. And to prevent these balls from aggregating together, they're passivated with inorganic shells, which are typically organic molecules which bind to the surface. And these shells are important because if you have regions of this inorganic material that aren't passivated correctly, they could create trap states. So in a generalized band gap, if you have a perfect passivation scheme, it's expected that you can get bright absorption and luminescence from the lowest energy transitions. Whereas if you have trap states, where you have unoccupied surface vacancies, they can introduce mid-gap trap states, which are optically dark and act as non-radiative recombination centers, or as heat, which are undesirable for practical applications. And so the motivation for incorporating these materials into optoelectronic devices is that their electronic properties are highly tunable. So going from bulk materials to more and more confinement, the energy levels become much more discrete, and you can change the spacing between these energy levels based on their size as well. So their electronic levels are highly tunable, but then you can also try to tune the kinetic properties of charge carriers in these materials. So one known method is through carrier-carrier interactions, which I'll gloss over, but essentially you can create from one single excitation in the right scenario, you can create two charge carriers, which would increase the photocurrents. So you get more power out of your cell that way. And another way is through carrier lattice interactions. So if you have free electrons or holes in a material, it interacts with the vibrational modes of the material. And for nanomaterials, it's known that the greater the confinement, the greater the spacing between the energy levels. So these little black bars in the diagram, and that if you just consider resonant and non-resonant transitions, if the energy spacings become much larger than the vibrational frequencies, it's going to slow down the hot carrier processes. And if you could slow them down enough to where you could extract those charges before they completely thermalize, you can break assumption one, which I mentioned earlier, and increase photovoltages. And so most of my research will focus on these carrier lattice interactions. And the specific material focus is the lead halide perovskites, which have become popular over the past decade plus in the energy community. So just a brief timeline of this material. So they were first characterized in 1958 in their crystal structure, and their lattice is shown in the figure below. So it's made up of 3 components. So it's lead halides and then various A cations. But the main, their electronic properties are mostly described by these lead and X anions. So the lead coordinates octahedrally to the halides, which are these X's. And then the lattice is quite unstable with just those, so you have to put in these A cations to induce stress to keep the lattice stable. And there's various publications looking at electronic and optical spectra for these materials up to 2009. But in 2009 was considered like the first report of somebody trying to use these materials in a solar cell, and they got reasonable efficiency in a dye-sensitized solar cell. And that kind of caused an explosion, where you can see that from 2009 to 2018, there was kind of an exponential increase in the publications, because people were finding that you could get people were getting improved higher and higher conversion efficiency. So in 2015, there's up to 18. I think up to now, people can get them up to 24% in lab settings, which would be comparable to like commercialized silicon. So initially in the solar cell community, these became popular, and then that also motivated people to try to make various nanomaterials out of these. And in 2015 was the first publication of lead halide perovskite nanocrystals, which are shown on the left, which are these little cubes. So they're physically realized particles in a box. And the reason that they're interesting is that based on the chemistry, so it's switching out halides from chlorine to iodine, you can cover their luminescence across the entire visible spectrum from blue to red. And if you notice that they have fairly narrow line widths too, which is particularly important for reds, those are hard to come by in that spectral region. And if you convert these line widths into a chromatic scale, illustrated here, so this is generally used to compare the color purity between materials. And so the boundaries represent the most color pure that you can have. And these white lines represent the technology standards for which are used in displays like televisions. And you can see that the perovskites are much, much purer, so these black dots. So the main takeaway is that the blues are bluer, the greens are much greener, and the reds are much redder. So they show a lot of promise for technology applications. And so initially when I started my research into this field, a couple of the holes in the literature were the impact of spin-over coupling on the carrier dynamics, because lead in these materials make up most of the conduction band edge states, and they're 6p orbitals, so they have very strong spin-orbit coupling. So it was kind of a challenge to update dynamics to include these effects. And so in terms of the material itself, the surface chemistry showed to be very liable. So what's shown here is a sample of purified lead halide perovskite colloids in Dr. Hobby's lab. And from another paper, they tried various solvents and ways to process these. And it's shown that just by putting them in different solvents, you can essentially kill the materials, and that's attributed to their dynamic surface chemistry. And so there are groups investigating how to get more stable binding and just understand the processes that happen on the surface and how it can impact the photophysical phenomena. And then the last topic I'll overview is their defect tolerance, which has been attributed to polarons that form in these materials. So in the photovoltaics community, they noticed that these charge carriers had very long non-radiative lifetimes and long diffusion distances, despite very poor conditions where they're synthesized, which give rise to a lot of defects. And people have thrown around the idea that polarons might form in these materials due to their soft lattice and polarizable lattice. And one paper that caught my eye was a group that looked at the temperature quenching that happens in films of these materials. So at low temperatures, they noticed that the luminescence was very bright, but at high temperatures, there was quenching that goes on. And so if there's quenching is usually associated with localization, which is illustrated in this figure, where the electrons and holes interact with the positive and negative anions and cations in the lattice and form various little potential wells, which trap the hole in the electron, which are these blue and orange regions. And they figured, these things should be spectrally active, and that the transition energies should be in the IR range, since they're like interband transition energies. And so they tried to turn this polaron into free carrier, and they see that at increased temperatures, they see increased signal, which they attribute to additional polarons forming. So that seemed like good evidence to me that they are happening in these materials. And so just to summarize what the research subjects that I'll be covering in the next couple of slides are my studies is the impact of spin orbit coupling with charge carrier dynamics and the influence of polarons and surface chemistry on the dynamics as well for this atomistic model of a nanocrystal. So quickly, I'll go through the methodology used to do the atomistic modeling. So first we start with electronic structure, where we get our electronic states. And this is done through density functional theory. Or instead of focusing on the wave functions, that the main quantity is the electronic density, so psi star psi. And clever physicists realized that from the densities, you can write effective potentials for the interactions between the electrons in the lattice, and that you can write like a single particle analog of the Schrodinger equation to get new orbitals. And from these new orbitals, you can make a new density, and you can make a self-consistent algorithm, which is shown on the right, so that you can get optimized geometry structures. And so the main takeaway from DFT is that with it, we can get good approximations for electronic eigenvalues, so energy levels for the dynamics, and we can get eigenstates or orbitals to compute observables for the dynamics. The first observables I'll talk about is light matter interactions, because if you're talking about a solar cell, you have to describe how the material absorbs and emits light. And so the goal is to compute transition dipoles, which essentially describe the interaction between an electronic state and a classical electromagnetic wave. And I guess I'll mention we operate in the independent orbital approximation, so we just consider pairs of transitions instead of superpositions of excitations. So we neglect excitons in our experiments, which is a valid approximation because in the strong confinement regime, they're less important than the confinement of the charge carrier. And so for the non-radiative dynamics, we have to compute electron-phonon interactions, which the main observable is these non-adiabatic couplings. And so the goal of these couplings is to determine vibronic frequencies, which mix together various electronic states. And so one possible method is to consider normal mode analysis, like a Hooke's law for springs. But instead, for the work I've done, we've opted for an on-the-fly method, which is where we use molecular dynamics to get the vibronic frequencies. So the ions are treated as classical particles and propagated using Newton's equations of motion, so F equals ma, where the forces come from the Kohn-Sham equations. And then we can set the velocities to a thermostat so we can control temperature of the dynamics as well, and use that as as a parameter for experiments. And so then the main observable is along the trajectory, we can compute these VIJs, so these non-adiabatic couplings, which is the changes and overlaps at adjacent time steps. And so from these couplings, we incorporate them into excited state dynamics formalisms. And so for equations of motion, like a well-known method would be for describing dynamics is the Schrodinger equation, but it's not, in Schrodinger equations, it's not straightforward to include dissipative dynamics, so electron phonon interactions or exchanges in energy. So we use density matrices for a formalism, which was developed naturally to describe open systems, so an electronic system interacting with a thermal bath. And the main quantity in these density matrices is these R dissipative terms, so these Redfield tensors. And I'll take a slide or two to describe these in detail. So here is a visualization of the Redfield tensor, which controls the population dynamics for charge carriers. And these are obtained from processing the non-adiabatic couplings into correlation functions and then Fourier transforms. And so what this tensor represents is the x and y's are electronic states, and the z components are rates of transitions in inverse picoseconds. And so maybe a more intuitive way to consider this figure is that it can be broken into blocks. So in this upper left panel, so the blue bars represent valence to valence transitions in the valence band, and these yellow bars and slightly green ones correspond to interband transitions in the conduction band, so conduction to conduction. And the VC and CV are non-radiative recombinations, and those aren't visible on the screen because they're orders of magnitude lower, so you don't see them, but they are there. And so with these tensors, we can choose initial conditions and then propagate dynamics. So LUMO plus, so this is just an example of starting from a LUMO plus 9 orbital and then propagating the dynamics until it reaches the LUMO orbital, so thermalization. And so on the left is the most formal way to describe these processes, but in practice, we break the densities into occupied and unoccupied and the Redfield tensor into its block form. And as an approximation, we decouple the intraband and interband. So we only keep the intra bands because they're much, much faster than the non-radiative recombinations. And so it can describe the cooling processes. And I belabor these points because later I'll show a way to try to reintroduce these non-radiative recombinations into the dynamics. So that's an overview of the methods. And before describing the studies, I'll quickly run through how the model was made. So the material of focus is cesium lead bromine perovskites, and they have a general form of ABX3, and its unit cell is shown in the middle. And replicating the unit cell a couple times in X, Y, and Z directions. This is the inorganic core, but then to have a healthy nanocrystal, we have to passivate the surfaces. And since these are ionic, we need combinations of anions and cationic pairs. And from experiments, the most likely are bromine or carboxylates anions. And for cations, it's cesium or ammoniums. And for the first couple of papers, the workhorse model is ammonium carboxylates to passivate the surfaces. And overall, this gives a nanocrystal on 2 nanometers in size. And so now I'll get to the first study for this presentation, and the motivation is essentially described in the introductions to see if these nanocrystals in the strong confinement regime we can see the slowing of the charge carriers and potentially extract hot carriers for solar cells. And the main summary is that it's not just confinement that's needed, but strong confinement plus with large spin orbit coupling, we can observe the slowed electron cooling, which seems to match with experiment. So quickly go through the technical challenges. So lead ions contribute 6p orbitals with large spin orbit coupling, and we can upgrade our DFT methodology to include these interactions in the non-collinear frame. So instead of using normal DFT, the non-collinear effective potential is a 2x2 matrice, which represents different spin configurations. So you have spin pure, so the diagonal elements, and spin mixed, the off diagonal. And with those, you can include spin orbit coupling interactions, or these L.S's terms mix the spin states. And then overall, they give two component spinners, which are composed of superposition of up and down spins. And so this is all relatively been known and implemented, but the novelty is to use these to compute observables for the dynamics. And we'll notice that they have a very big impact on the electronic structure. So on the left just shows density of states without spin orbit coupling, which has a band gap of 3.1 eV. And when you include spin orbit coupling, the band gap shrinks to 2.38, so a change of 0.7 eV. And that's due to the large spin orbit coupling of the leads, which make up the conduction band. And you'll notice that the density of states near the valence band edge gets more stretched out, which will be important for the dynamics. And so to go through the dynamics, we implement molecular dynamics first. So this left figure is the jiggling atoms, which give bond vibrations. And on the right shows the changes in cone-sham orbital energies due to the vibronic interactions. And along this trajectory, we compute these non-adiabatic couplings in the spinor formalism. And then we get Redfield tensors that looks like this for this specific model to control the state-to-state transitions. And then for initial conditions, we choose a state which has a bright optical feature, so HOMO -9 and LUMO +10. I'll note that you can see for the electron, it mostly interacts with the lead 6p's, so this blue line, and the hole interacts with a bromine 4p and lead s orbitals, along with some contributions from surface states. And so we implement the dynamics, and instead of showing propagations of populations, we show the change in energies of these charge carriers over time. So the x-axis is a log scale, so 0 is 1 picosecond. And the color scheme is changes in density. So green is background neutral, blue represents a hole, and the orange represents an electron. And we can see that after the initial condition, they dissipate their energy to the HOMO and LUMO, or the valence band edges, on a sub-picosecond timescale. And if I had a higher resolution image, you would see that there's a smearing here as it cools down, which is an interesting feature. So to examine that in more detail, we focus on this dotted black curve by plotting it on a normalized scale. And so that's what this figure shows here. So this black solid line is the dotted line from previous. And the red dotted line is just a single exponential fit to it to give some contrast. And on the right shows the density of states between the initial state and then the final state. And we can see that there are two regions of cooling. So there's a faster component at the higher energy regions and a slower decay at the lower. And this change in fast to slow we attribute to this large subgap in the density stage, which is about 200 millielectron volts, so which is much, much larger than thermal energy, which is like 30 millieV. And to show that this cooling is due to spin-orbit coupling interactions, we compare it to calculations without spin orbit. So it's a similar transition energy, but there are much larger density of states within these regions, and we get 2 orders of magnitude quicker decay. And so overall, where this study fits within the context of what other people have done. So there was a competitor group who did similar calculations with slightly different methodologies, similar models, and they observed a similar trend of slower cooling near the band gap. So that makes me feel a little reassured that our methodologies were seeing something correct. And then there were other groups that tried to incorporate spin-orbit coupling, but for bulk materials instead. And they found that in bulk that it accelerates the non-radiative dynamics. And when I presented this study at a conference, one of the main authors on this paper seemed fairly disturbed that our abstracts had different titles. Mine says it should go slower. It says it should go faster. Well, who's right? Well, I think it turns out that we're both right. From the experimental study that I mentioned earlier, where they measure carrier cooling dynamics for various systems. So going from red to blue goes from large to small nanocrystals. And in their experiments, like the smaller nanocrystals showed a much longer decay times, and even seems to slow down closer to the band edge. Whereas for the bulk, it's the carrier cooling happened much quicker than the resolution time could even allow. So it seems that these results kind of give a good overlook of the non-radiative processes in these lead halide perovskite materials. So where am I at in time? So that was study 1. Study 2 is a case of trying to predict materials property. So motivation, I'll try to walk you through like a quick thought experiment. So for photo excitations, after the initial excitation, it takes time for the lattice to reorganize around the charge carriers. So there's a polaron formation rate that's on the time scale of these cooling rates. So they're competing with each other. So you can consider 2 scenarios where if the cooling is much faster than the polaron rates, this electron will lose all of its energy and then reorganize into this polaron potential well and be in its polaron ground state. But if you consider the opposite scenario, where the polaron formation happens much quicker than it can cool, this electron will lose a little bit of energy, but then once it forms into this potential well, it will be in like a polaronic excited state. And so in this excited state, there's a population inversion between this P and S, and the transition frequencies are in the IR range. So is it possible to see infrared emission from these states? And so that's kind of the mindset for the next set of calculations I'll describe. And so I'll run through this. So to describe polarons, we essentially add or remove charge from our atomistic model. So in the ground state, so n electrons, we get a set of ground state nuclear coordinates. And with plus or minus n charges, we get a set of nuclear coordinates due to polaronic reorganization. And to visualize this is a 2D projection of a hole added to the model. So it has a different charge density, and you have yellow arrows describing the changes in nuclear coordinates due to this hole presence. And so to see what their transition energies are, we can look at the density of states in IR spectra. So the top half of the panel is for negative polarons, where the Fermi energy is shifted into the conduction band. So you have occupied S states, which can have transitions to P and D. And those are shown on the right as these little arrows. And their transition energies correspond to 1500 wave numbers, which is like mid-IR region, which is, I think, about 5,000 nanometers. And we can do the same thing with the positive polaron. So creating a hole and reorganizing it, the Fermi energy shifts into the valence band. You can have these same S to P transitions, and their transition energies correspond to like 500 wave numbers, which is far IR region, like 10,000 nanometers. And so we have an idea of the energetics involved. So to look at the kinetics, we run through the same machinery as molecular dynamics to get to Redfield tensors to describe population dynamics. And I'll jump straight to the radiative dynamics. So these blue figures represent time resolved emission. So the green figures from previous were non-radiative transitions, but here these are radiative. So the blue background is dark optical signals, and the yellow and green features are optically bright along the trajectory. And so these are time resolved spectra, and we can integrate them, which are shown to the figures on the right. And their spectra are dominated by these P to S like transitions. And we can see that the negative polaron on the top has a higher intensity than the positive polaron. And so we compute intensities, but we compute rate constants, so we can try to calculate a theoretical yields for these luminescents. And disappointingly, they're fairly low. So like 1% would have been something that could have been promising, but we see much, much lower. But the interesting feature is that there's 3 orders magnitude difference between their photoluminescence quantum yields, which should raise some question marks, which could give such a big discrepancy. And it seems to be due to these non-radiative transitions. So if it's non-radiative, there's probably phonons involved. So what we do is we plot the phonon density of states, this top black panel, with the transition energies from the negative polaron, the middle panel, and the positive polaron, the bottom panel. And essentially the main takeaway is that the negative polaron has off resonance vibrational modes, whereas the positive polaron is more in resonance with the low energy transitions. And so off resonance gives you much slower relaxation and the large difference in the yields. And finally, I have about 5 or 6 minutes to go through the last seminal study. So the motivation for this study starts with an on-campus collaboration with the Dr. Hobbies group. So what we did is we synthesized these lead halide perovskite nanoparticles and processed them into size resolved fractions. So we can see that the bottom of the tube has large nanocrystals, but at the top of the tube, they're smaller and they have very low polydispersity. So there's no changes in size. And if you look at the luminescence decays, there is a clear stretched exponential going from large to small, which is indicated by these downward sloping triangles. And when you have a stretched exponential, that's usually indicative of having a large distribution of recombination pathways, where if you only had one, it would be single exponential decay. And so we think we have calculations that show this is due to the defect tolerance of lead halide perovskites, where due to polaronic reorganization, we get bright surface electron trap states, is the main summary. So to quickly overview how we did the calculations, we first considered 2 models in 2 different electronic configurations. So I mentioned pristine models, so they have no defects. So we do it on the ground states, and we also do a calculation on the lowest excited states, which is meant to approximate the lowest energy photo excitation. And then we do 2 more calculations, but in this case, we consider a surface defect model, and we optimize one on the ground state and one on the lowest excited state. And by a surface defect, it can be visualized here. So it's a zoom in of the surface, and the red dotted region, of course, shows where the vacancy is, where we remove a bromine and an ammonium as a leaving group, which is a likely leaving group from experiments to leave a defect. And so for this case, this ammonium bromide model will be the workhorse. And the main takeaway from the pristine defect-free surfaces is that in both the ground state and the lowest excited states, where we add a electron in the conduction band and a hole in the valence band, the charges remain delocalized throughout the model. So it's free from trap states. Whereas when we consider the surface defected model, where on the left we show the defect with the red arrows, or the red dotted circle, and that in the ground states, the band gap still seems pristine. Whereas when we optimize on the lowest excited states, there is a state which enters inside the band gap lower than the SE and SH orbitals, and this mid-gap state is localized to where the defect was removed or created, and is localized on the surface lead. And so due to polaronic reorganization, this defect state is stabilized by the occupation. And typically, you would think that these defects are optically dark because it localizes density to the surface. But we see that these states can have relatively bright signal compared to the pristine samples. So the figure on the right shows red, green, and blue. It's for the ground states where the orbitals look nice and delocalized throughout the model. But when we consider the defected models, so the excited state, these pink and light blue ones, the luminescence or this feature gets quenched, and there are red shifted peaks which we observe. And these red shifted peaks are these SH to surface trap states. And so in terms of dynamics, can we get bright luminescence from these trap states? And I'll quickly run through the methodology updates to introduce dampening back into the equations. And so essentially we make a clever substitution for our densities, which includes an exponential decaying term depending on the recombination rates. And we can show that we can remove the off-diagonal matrices and put them into a prefactor, which represents the decay or the dampening. And just to illustrate this with the non-radiative green figures, so normally these red and blue lines would extend infinity to how long we ran the dynamics, but now they decay in time, so they become less intense, which represents the recombination. But in practice, or for this model, we're more interested in the radiative dynamics. So we go back to these blue figures, the time resolved emission, and the charge carriers relax to the band edges on a 10 to 100 picosecond timescales. So for the pristine surface, we have luminescence, and in the integrated luminescence, it's the most prominent feature. And in the defected surface, the most prominent feature is the surface trap to a hole state. So it has the most intense luminescence along the trajectory. And when we consider efficiencies from the radiative and non-radiative rate constants, we can see that the pristine surface has near unity luminescence, and the surface trap state is degraded, but is still fairly high at 75%. And I'll note that these dynamics were done at the lower temperature, so 77 K set a room temperature, so it's liquid nitrogen conditions due to technical reasons. But so these numbers are likely inflated, but the fact that we do see fairly bright luminescence is a promising sign that they could be bright in experiment. And I guess I was going to mention that it could correspond to Stokes shift, which are observed in experiment as well. Or for these experiments, or for the simulations, the Stokes shift would be around 180 millieV. And in experiments, for smaller crystal sizes, they increase into the 100 millieV scale. So it could be used to possibly rationalize Stokes shifts as well. And so that is the end of my doctoral dissertation presentation. And I'd like to give acknowledgments to a wide cast of groups, so specifically the Cullen group and Dr. Cullen in particular for providing a stimulating work environment. And I'd also like to thank our collaborator, Dr. Innerbev, who has always been helpful in keeping Fortran codes running smoothly and helping generate couplings for some of the papers that we collaborated on. I'd like to thank Dr. Kalina and Krajewski groups for stimulating group discussions over the years. I'd like to thank Dr. Hobby's group and Eric in particular for allowing me to expand my horizons and get my hands dirty with trying to make and characterize the samples. And I would like to thank the Lino group and Dr. Newkirk in particular for being willing to work through the craziest of last year and taking me on as a summer student again this summer. And so with that, the floor is open to you all.
Okay, please join me in thanking the candidate, Aaron, for presentation. And the thesis is open for discussion. So please, if no one is speaking, please feel informally invited to speak. If there will be multiple volunteers to ask questions, then raise hands with the Zoom facilities. So please, paper is open for discussion.
I have a public question, if I may.
Please.
I would like to ask about the defect tolerance in relation to polarons. Some of the audience might not be familiar with the concept of a polaron. Could you describe that in a little more detail? In particular, how does screening enter the problem?
Yeah, so it's I'm trying to find a slide which gives a helpful cartoon to understand the polarons. But while I try to find it, so polarons are an interaction between a charge carrier in a lattice and the lattice vibrations itself. And so in traditional semiconductors, the bonds are covalent and they're not polar. So the lattices don't really create dipoles that the charge carriers can interact with. But in lead halide perovskites, you have anions and cations, so positive and negative charges, and they're very polarizable. And so if you put a carrier into the lattice, with this green region, it's going to attract positive ions, so cations. So cations are going to want to be attracted to that, and anions repulse them. And so you have essentially a dipole reorientation around the charge, which screens it from the rest of the lattice.
I see. So it is all about screening then. Yes. So then I have another question that leads into these, as we know, you and I very well, are notoriously soft materials. Is that a consequence of the ionic interaction, or is it a consequence of the perovskite structure itself?
I think generally it's due to a large part of it is the ionic component, since they're polarizable. So by definition they're able to move easier, and their bonding is less direction oriented. So if you apply stress, it's going to have more strain just because it can reorient more.
Okay, I see there is a typed question from the audience. So, Professor Svetlana Tilina, would you like to verbalize your question?
Oh, for the vacancies, when you were talking about creating the bright surface defects, so you mentioned that you're taking cation and anion. I'm just curious, both of them has to be taken together, so you will have a neutral structure to have this bright defect, or it doesn't matter, you can take them separately and you still will have a bright defect.
Yeah, that's a good question. I think so the main defect that forms is when lead is undercoordinated, because the electrons are mostly made up of the lead 6p orbitals. So whenever there's a vacancy for the lead, that's when the defect forms. So it's, in principle, I could have just removed like a single atom, but then there are issues with charge balancing. And I guess you're a chemist by training, so if you look at the various pairs of ligands at the surface, they are conjugate acids and bases, so they're highly dynamic with each other. So if there were defects to form, they would likely leave as groups corresponding to those acid-base equilibria.
So, in short, you're trying to say that you think it's impossible really to have, like, to take only NH3 plus, or just to take only carboxylate group, right? Because they're kind of really in balance, and they both either there or they both gone when defect is created.
Right. It's much, much more likely they leave in groups than as individuals.
Okay, thank you.
Aaron, may I?
Yes.
Sorry. Sorry for being such a nerd, but there is a very helpful slide at the rather beginning in the introduction where they introduce time-dependent Schrodinger equation. Can you please go back to that? I have more questions, but I'll ask them in closed session.
Okay. So, any questions not from the committee? Yes, Professor Klina, please.
So I maybe missed this part when you explained your computational approach and the overall kind of overview the theory, but in several places you refer to the, like, for example, when you were showing your density of states, I mean, the density of states of the systems you were considering. So you talked about ground state and excited state density of state. And then also for spectra, there was pretty much the same terminology, ground state, excited state. So I'm a little bit confused. I think I might understand what you mean, but maybe you can give a little bit better explanation once again for what you mean by the ground state. What is that? What do you mean ground state absorption spectra? Like you show in absorption spectra and calling ground state. This is very confusing because it's already excited. How it can be ground?
Yes,
And the same for the density of states. You show in excited state density of state, or what is it?
So in terms of density of states, so the main distinction, so my screen will show it.
I think it was not on this slide, right? It was where you really have these names, excited, ground state, together. Yeah, something like this, yes.
Yeah, so a better way to describe these light blue and pink features would be more of a bleach than an absorption. That makes sense?
Not really. I'm just asking, what do you call ground state? When you show in the spectra, you call ground state. What does it mean, ground state spectra?
So it's the
because by definition, you cannot have absorption spectra at the ground state.
Right. So we make an approximation where the ground state electronic structure doesn't change with the photo excitation. So ground state refers to, we use the ground state's energy levels.
I see. So it's probably better to call it single particle approach, right?
Mm-hmm.
You kind of use single particle without really inclusion any changes due to the interaction between electron hole pair, right? So then, and well, what you call excited states, and what does it mean? How exactly you calculate this excited state? Maybe you already mentioned it in your theory, part? Maybe if you just go to the theoretical part and just overview it once again.
So it's not as much related to theory. It's more notation for the specific model. So by excited states, I mean that when we look at like our approximated excited state density of states, where we add an electron manually to the LUMO and add a hole to the HOMO. So that's what we call, that's how we approximate the lowest excited state. And then from these energy levels, we compute the dipoles and everything to generate the spectra.
I see. So just kind of non-equilibrium population of the lowest state, your homoluma state, kind of to mimic. I would say it's probably close to the idea of single CI configurational iteration scheme, but instead of really going through the all possible formation of the excited pairs, you just really kind of focus on which will contribute with different coefficients to the actual excited wave function. You just kind of include only consideration of the lowest electron hole pair contribution.
Mm-hmm.
I see. Okay.
Yeah, and I think.
And do you have any evidences with direct experimental comparison for let's say absorption spectra or something which will justify this approach?
Yeah, so the comparison would be to compare like the spectra we compute to something higher level, like TD-DFT or Bethe-Salpeter. And it hasn't been done for the models in question, but in a more general framework, since in the strong confinement regime for the nanoparticle, it's the Bohr radius is like 8 nanometers, and here it's 2 nanometers. So you have contributions from 1 over r squared and 1 over r. And the 1 over r squared is more dominant than the Coulomb.
Okay, but you didn't really have a comparison of this approach to this method. I mean, this method applied to this system versus higher level methods to the same system. You just refer that this comparison was done on a smaller models, and they show a good agreement with the only confined systems. Okay. And since you were doing experiment, I thought you can directly compare the data from experiment to your computations, let's say absorption spectra or something like that.
Yeah, I mean, it is possible. I know we did it for one of our papers, but that was with the monodisperse samples. So we saw a couple of peaks which look similar in trend, but then there were additional peaks in the experiment which were off, which we think is just due to the distribution in sizes.
Okay, thank you.
If I may I?
Please.
While we're on the subject of absorption and such, can you remind me, please, what is polaron absorption? It should be somewhere nearby these slides. So photon goes into what? What kind of final state does it create?
I assume you're referring to my methods slides? Or do you mean like
could be one of your projects? Should see if you number the slides, actually, which you did, but I looked and I couldn't see the number. So it says it's a slide where it says positive polaron absorption, negative polar. Oh yeah, this one. But very basically, so photon goes, let's say, into electron hole pair, excited state. What does it go into in this case? When we're talking about the negative polaron absorption spectrum, positive polaron absorption spectrum? What is the final state? It's not a trick question, just remind.
Well, it's, in these calculations, it would be like a pseudo electron hole state, because we compute matrix elements of the transition dipole.
No, I mean, very qualitatively. I mean, is there an electron and hole here? And if not, is it some kind of modified electron and hole or something like that? And how do I think about it?
I would say modified electron hole,
Okay.
because so this figure on the far right, so this PE band. So we assume that if we have a hot polaron, this band will be occupied with an electron. In this SE band, it would be an analogous hole state, which it can annihilate with.
Okay, I see. Okay, thanks.
Can I briefly ask complementary question? This figure refers to the notation SE, PE, DE. Is there a definition or maybe visual explanation of what they are? The notations of this SE, PE for.
Mm-hmm. Yeah, so they come from originally atomic physics. So if you consider electron orbitals, the lowest energy will be spherical, so that's S shape. So that's S, and you also have p orbitals, which have nodes in them. So those are labeled as p, and those are analogous to the envelope functions for the nanocrystals. So they refer to symmetry of the envelope.
Do you have an illustration of this?
I do in my supplemental slides, and I saved those in separate deck. Oh, here we go. So for conceptual analogy, S and P refer to like a particle in a box, like these circular blobs and these dumbbell-shaped yellow blobs. So S refers to spherical, so the circular orbital, and then P refers to these dumbbell-shaped orbitals. And from DFT calculations, I looked at the envelopes from the wave functions that were computed, and just tracing out the envelope, you can see that the SH looks really good for spherical symmetry, where the SC has some polarization, but I mean, it's an atomistic model, so everything can't be perfect.
This tracing out, friend, chiming in here.
Mm-hmm.
Is it something that's included in DFT software? Is it something, some kind of keyword you have to do in VASP?
So the highlighted section I have is what VASP gives you, so it gives you a charge density.
Right.
On XYZ, and then manually. Yeah, so I take those orbitals and project onto one axis by integrating.
Okay.
Charge density.
Okay. All right.
Can I ask some questions? Yeah.
Oh yes, please.
Oh, okay, good. Thank you. So, so first question is in the beginning of your presentation, you talked about nanostructural materials. So 2-dimensional, 1-dimensional, zero dimensional. nanomaterials. So how those contacts are related to your work, or in other words, did you take into consideration what the structure or nanostructure when you did those simulations?
Yes, thank you for the question. So I believe this is the slide you're referring to, and specifically for this dissertation, I focused on the 0D version. So if you put charge carriers into the 0D materials, they are confined in X, Y, and Z directions. And I just considered a different chemistry of 0D material.
Right. Likely you are talking about the quantum effect, right?
Mm-hmm.
So you get so that's a related question is that how do you think that nanostructural materials can benefit solar cells? Yeah. We really want to use the nanostructural materials for solar cells or not, or we really want to make materials into quantum dots.
Mm-hmm.
Yeah. If we want to, if we consider solar cells, yeah, how do you answer this question?
So in the literature, I've seen two different ways,
right,
to try to use these 0D materials of various chemistries. So one is through utilizing their carrier-carrier interactions, which I'll skip the fine details, but the main point is that with a single photo excitation, it's high enough in energy compared to the band gap. You can generate multiple charge carriers, and that would increase your photocurrents and increase the theoretical yield of the cell.
Okay, so yeah, go ahead.
And then another way is through these carrier lattice interactions. So in quantum dots, it's been not long, but it's been theorized that you can slow down the carrier kinetics and extract hot carrier.
Okay, so let me ask you in this way. So if you make a material into quantum dots, so you will get smaller band gap or larger band gap compared to the bulk material.
Large.
Yes, very large, right?
Mm-hmm.
But for solar cells, actually, we want to narrow band gap, right? So you talked about the carry-to-carry interaction, some improved interaction, some of that, but you didn't take into consideration with light absorption first, which is actually related to the band gap.
Mm-hmm. Yeah. So
right.
So it does. So yeah, you do still need favorable band gap in the redder region, and there are established nanomaterials like I can't think of which specific combination, but like cad selenide or cad sulfide. One of those has very low bulk band gaps, and when you quantum confine them, optimal range.
Yeah, I think that's also a reason you can see that the simulated band gap in your case and also in literature for this material it's about 2.4 electron volts. Mm-hmm. But in practice, actually, the band gap of the material is should be below 1 electron volts, right? Mm-hmm. For the materials used for real solar cells. Yeah. So yeah, that's just my question. Yeah, I want to remind you if possible, you may want to include the quantum effect into the simulations if possible. Yeah, obviously there may be quantum effects when you do the simulations because you didn't take a very large enough unit, right? Yeah. Okay. Yeah. Thank you.
Thanks.
So another questions from general audience. So please feel free to ask questions verbally.
May I ask one question?
Yes, please.
So in fact, as far as I understood, you calculated some influence of suffix atoms and surface defects of the relaxation processes in these quantum dots, and you used only one size of your quantum dots. Can you predict what will be observed when the size of quantum dots will be higher with the same defects?
Yes, thank you for the question. So it's just based on surface to volume ratios. At bigger size, the surface effects become less important or more neglected. So I would expect that like those shallow trap states should start to disappear with bigger ones. Maybe not totally disappear, but become smaller in energy.
Mm-hmm. Yeah. So in fact, to my mind, as I have to say, the spreading of electron wave function becomes smaller when we increase the size of quantum dots. It means that the quenching effect, the quenching processes, will be sufficiently diminished in this case. If the size of quantum dots will be higher, with the same number of traps and the energy, or not?
I didn't completely. So you're saying that you suspect trap states become more important or less? Or so your intuition is more important?
Yeah. Okay. Thanks.
I have a question too, if you.
Yes, please.
It's a very impressive presentation, very informative. My question has to do with the type of functionals you have been using to calculate band gaps and relaxation times for perovskites. What kind of functionals do you use, and how sensitive the band gaps are, and also the relaxation time to the functional type?
Mm-hmm. Yes, thank you for the compliment and the question, Dr. Mitra. So for all of our calculations, we do PBE because we have to essentially do thousands of calculations, and doing more expensive functionals will be time prohibitive. So we stick with PBE. But for SHC, it's known that PBE underestimates, and if you include hybrid functionals, the band gaps should correspond better to experiment. And I think the more important aspect for the carrier dynamics is that the changes in energies between, like in the conduction bands and valence bands, aren't as drastic. So there is still an overestimation, but I think overall the computed rates will still be qualitatively similar if we used more expensive functional.
So if you compare the hybrid functionals with the PBE functional, the results are somewhat similar. Is that your conclusion?
I guess, yeah, the band gaps definitely increase, but the intraband transitions are still comparable.
Okay, thank you very much.
Okay, Professor Krzyzewski, you are ready.
Follow up since we're on this topic. I mean, you have to approximate DFT functional, as we all know, and there are all sorts of approximations. But are they supposed to produce you the correct band gap? Well, you just answered this question. What is it that you're supposed to do to get the correct band gap? Just give a name of, I don't know, technique that is rather common.
Well, I guess they're not changing functionals, but change in methodology. That's what you're asking?
Well, you do what you have to do to get things right. So first you do DFT, and then you do what? To get the correct single particle band gap. you know, in an ideal world, if you had like infinite amount of computer time, or if you are after high accuracy, high precision.
So in DFT, the electron Coulomb or electron hole interaction is not accounted for. So to reintroduce that, you can do a TD DFT or Bethe salpeter.
Okay, that's one. So it's, you see, Bethe-Salpeter equation is a technique beyond DFT.
Right.
What is another technique that is specifically germane if you want to get correct gap, correct single particle gap? GW, you ever hear of GW?
Yeah. Okay. Yeah. So it's wasn't that used as an input for Bethe salpeter?
Yes. So as the as it goes, first you do DFT, then you do GW, and then you do Bethe salpeter on based of the previous results. It's just that you're quoting gaps. You just showing DOS from your DFT runs, and there should always be a disclaimer that I know that just because of the computer time limitations or whatever, there is a systematic uncertainty in there, just because your technique is not perfect. So I was just trying to get you to say that yes, we're not doing GW. Yeah, we realize that. So we're looking for qualitative trends and all that.
Yes, that makes sense. I did for the smallest model I could possibly make. I tried a GW once, and
yeah, no, it's not fun.
The memory allocations were crying all the time. So it's like, oh, I'll move on. But yeah, I see your point that band gaps with DFT are mostly unreliable.
Okay, let's check if there are more questions. So please join me thanking the candidate and all attendees for wonderful questions and support of this event.
Nice job, Aaron.
Thank you.
All the audience for coming.
And
with YouTube. So I'm thankful that you spent your time here.